Hello, Tent Triple. We're carrying on with pressure and volume and temperature calculations. We did have a look at this last time, the gas laws. A gas, if its temperature stays the same, and there's our gas there, if the temperature stays the same, if you double the pressure, you are going to halve its volume. Basically, pressure is inversely proportional to volume. So this diver here, their lungs are large, but when they've gone down a long way, the pressure has increased. So look at the volume of the lungs now. It's really decreased, hasn't it? Okay, this is an equation now that we're going to take this nice and slow because I don't want you to get confused. We've got a fixed amount of gas. And based on its pressure at the start and its volume at the start divided by the temperature, those values, P1, V1 divided by T1, will always equal, as long as we've got a fixed quantity of gas, a certain number of particles of it, then at the end, if you change anything about the pressure or about the volume or about the temperature, they're going to be equal. Okay? I'm just going to get rid of all of this information, all this colour again. All you need to understand is P1, the pressure, times the volume divided by the temperature at the start of an experiment is going to equal the pressure times the volume times the temperature at the end. We're looking at a fixed amount of the gas. Let's do a calculation now. Now, the only thing that you do need to remember is the temperature needs to be measured in Kelvin, K. Let's go through a couple of examples. First off, I'd like you to write this out, please. Okay, these four questions, question 1 and question 2 and question 3 and question 4, you do need to write out. Okay, so the first one is question 1. A column of air in a Boyle's law apparatus has a volume of 50 centimeters cubed at atmospheric pressure, which is 1 times 10 to the 5 pascals, or 1 times 10 to the 5 newtons per meter squared. And we've got a room temperature there of 293 Kelvin. If the temperature remains constant, I'm going to highlight that now. If the temperature remains constant and the volume is compressed to 30 centimeters cubed, what's the pressure of the air? Now, we're going to use this equation here. P1 times V1 over T1 equals P2 times V2 over T2. Now, I've written it down here as well. There's the equation. Always write it down. But it says if the temperature remains constant. If the temperature remains constant, we don't need these two. You can cross those out. So we've got a slightly altered equation. P1 times V1 equals P2 times V2. Now let's put these numbers in. I'll try and highlight them as I go along now. A column of air, we're looking at question 1. A column of air in a Boyle's apparatus has a volume of 50 centimeters cubed. So at the start, V1, the volume was 50. Now the pressure was 1 times 10 to the 5. 1 times 10 to the 5 pascals. And that equals P2 times V2. Now, P2 we're trying to work out. We don't know it yet, but we do know the volume. The volume has been compressed to 30 centimeters cubed. I hope you're with me so far. Now what I can do, is rearrange this equation to work out P2 on its own. And that will be 1 times 10 to the 5 was the pressure at the start, times 50 centimeters cubed was the volume at the start, and now we divide it by the volume at the end. It's been squeezed down from 50 to 30 centimeters cubed, which means the pressure has gone up. So the pressure is going to be larger than atmospheric pressure. Let's work it out. P2 equals, now I get this answer here, right, on my calculator, 166,666.6 reoccurring pascals, which if you want to put it into standard form would be 1.6 reoccurring multiplied by 10 to the power 0, 1, 2, 3, 4, 5. 1.6 reoccurring times 10 to the 5 pascals. And you can clearly see here that this new pressure is larger than the yellow original pressure, and its volume has been reduced. Anyway, there's the answer to question 1. Let's have a look at question 2 now. It's not easy. The volume of a free diver's lungs. So he's a diver without an aqualung. He's just going to go, he or she's just going to go down, and then the lungs are going to get smaller and smaller. At the top, they're approximately 6 litres, and the pressure is 1 atmosphere. So we've got the volume, 6,000 centimetres cubed, 6 litres. We've got the pressure, 1 atmosphere. Every 10 metres depth of water increases the pressure of the diver's lungs by 1 atmosphere. The world record free dive depth is 214 metres. Calculate the volume of his lungs. So that's what we're trying to work out. We're trying to work out his volume there. We can work out the pressure. I'll be going through that in a second. This is the mega important one. We are assuming that the temperature of his lungs stays the same. So we can cross out T1 and T2. So we get this equation here. That's what we're going to be using. P1 times V1 equals P2 times V2. So let's put the numbers in now. Pressure 1 at the start, 1 atmosphere, 1 times 10 to the 5 pascals, multiplied by the volume in centimetres cubed, 6,000. And we're trying to work out the volume when he reaches, I'm going to do that in a different colour. We're trying to work out his volume when he reaches 214 metres. Now, how do we work out the pressure at 214 metres? Take a leap of faith. At the surface, atmospheric pressure is 1 atmosphere. And then every 10 metres you go down, 10 metres, there's another atmosphere of pressure. So it's 2 atmospheres here. And if you go on to 214 metres, then you've got 1 atmosphere of pressure at 21.4 atmospheres of pressure. And that equals 22.4 atmospheres of pressure. But of course in pascals, that's 22.4 times 10 to the 5 pascals. That is how I have got this number here. If you then isolate V2 on its own, it will be one times 10 to the 5 multiplied by 6,000, and then you divide that by this number here. And when you do that, I'm just going to check this now. So I've just calculated the answer at 267.857, etc., etc., etc. So I've just rounded that up to 268, and the original volume was 6,000 centimeters cubed. So his lungs have been utterly crushed down to 268 centimeters cubed. I'm just going to work out the sort of percentage they've decreased. They're less than 5% of their original volume. Wow. You make sure you need to be writing down these questions and then putting the answers in. Let's move on to question 3. A tethered sealed helium balloon has a volume of 20 centimeters cubed. Volume is fine. It is inflated at atmospheric pressure and a temperature of 290 Kelvin. The gas burners are then used to heat the air inside to a temperature of 510 Kelvin. So there's a second temperature. If the balloon is allowed to inflate to atmospheric pressure, so in other words, atmospheric pressure stays the same, remove that from the equation, then calculate what is the volume of the balloon. We're after V2. So V1 divided by T1 equals V2 divided by T2. Okay, so we've got that equation there. And then we put in the values. 20 meters cubed divided by 290 Kelvin equals the new volume, we don't know what that is yet, divided by the temperature, 510 Kelvin. So rearrange that and you get 510. So the volume is going to be 510 times 20 divided by 290. And the volume equals, it's increased because the temperature has increased to over 35.2, and the units, be careful, meters cubed. Okay, got to be careful with these questions. Remember to write the question down. Let's move on to the last one. Final part of the lesson. Absolute zero, the coldest temperature. Let's condense these notes all the way down. Gases consist of particles. The higher the temperature, the higher the speed of the particle. Gas particles collide with walls of the container and they exert a force on the walls. The force acting over the walls creates a pressure. Pressure decreases as temperature decreases because the particles are moving more slowly. They're exerting a smaller force. Eventually, at minus 273 degrees C, all molecules stop moving. The gas does not exert any pressure on its container. This temperature is absolute zero. Absolute zero is 0 Kelvin or 0 K, or minus 273 degrees C. You cannot get a temperature lower than that. Now, we can convert from Kelvin into degrees using this formula. So let's convert degrees C into Kelvin. This first one will be 23 plus 273, which gives us 296 Kelvin, minus 57 degrees C. Add our 273 gives us 216 Kelvin. .486 degrees C is 486 plus 273, which gives us 759 Kelvin, and then minus 1 degrees C plus 273 gives us 272 Kelvin. That will be the end of this lesson.